Alright guys, in the last video we were talking about the old days, the good old days when cars used to be manual and I could go and, slap it in first and slap it in second and brum, 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 brum. But over a course of time, people just got kind of annoyed with manual transmissions and they began to get more automated, and then people just didn't know how to drive manuals because they were so used to automated ones. And now it's very rare to find a manual transmission or a stick shift in a vehicle. Alright, so with that said, we talked about manual control and automated control in the manufacturing process. So there are times that I have to go in and I have to manually do these types of things myself, and there's got to be a little bit of manual labor involved in order to do that. And then other times there's going to be things that are more automated. There's going to be computer interfaces that I will have to work with, like touch screens or actual computer and software, and they are going to monitor and track things for me so that way I can do something else with my job instead of just staying there and watching things heat, watching things change, and recording and logging information. So they can do that type of basic work. I've got better things to do with my life and my time. So see ya, have fun, automated instrument. So let me know when something goes wacky. And it does. So we talked about the alarms that can go off, and we said there's two different types of alarms. One is just an alert alarm, and that's letting you know, alert, 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 something's going on. And then some of them are action alarms, which means an action is going to be needed. So you've got to fix the problem, and in order to fix the problem, you've got to do something, a big physical change that has to happen, or these things are going to get worse and worse. So under the automated type of scenario, I'm going to call it the umbrella, you get a couple of different modes that the automated controls can be in. And that's the purpose of this lecture video. So one of those modes with the automated control feature is just a simple off and on. I mean, that's all that it is. So here you're seeing a type of control, and that is a light switch. So you either get an off or you get an on, and there's nothing in the middle, right? So these are called two-position controls, and the other term that they go by are going to be discrete controls, or off-on controls. And to be honest with you, most people are going to say off-on. I mean, I don't think I have ever heard someone go up and say, ooh, this is a discrete control. People just don't do that. So off and on makes sense. Off and on, people that aren't even aware of this type of control will get the idea that, oh, okay, there's just an on and there's just an off. There's no other choices. There's nothing in between that I get to choose from. And it's also called, of course, a two-position control for that reason. There's two positions, either off or either on. So these are going to be somewhat common. They are not, outdated. They're not things that people don't want. And the reason that I say that is because the two-position control, or the on and off, is pretty common for a lot of the situations that we find ourselves in. So everything from water heaters, heating and air conditioning units, pumps, rotating equipment, all of these off on, off on, off on, off on. There's hardly anything in the middle that we need to set. Okay, so now with that said, here at the very bottom of the slide, it says, to stabilize control and reduce switching frequencies, systems are designed to prevent control action during a specified period of time called a deadband. Folks, that came straight from your book. All right. So what on earth is deadband? What are they talking about? How does that even make any sense? All right. So let me give you an example. All right. One of your two-position controls is kind of like your thermostat and your air and heating system that's in your house. So what happens here is that you will often probably set your thermostat at a certain temperature. All right, so let's say, it's hot summer day in Wilmington. I don't want to be outside in 100-degree weather. Who wants to deal with that? I'm kind of redheaded and pale-skinned. I don't want to go out to a beach and get sunburned within 5 minutes, so I'm going to stay in the house. So I go into the house and I go over to my thermostat, and I set my thermostat at 74. Oh, nice comfortable temperature. All right, so my thermostat kicks on, and the inside of my house might be hot because it's hot outside. So my air and handling unit is going to come in, and it's going to take maybe my 81-degree house, and again, I'm talking Fahrenheit here. All right, I'm just going to take my 81-degree house, and it's going to start cooling it. And it's going to cool and cool and cool and cool and cool until it gets to, guess what? The set point. Oh, use your words. So there's my set point. And my set point, that's the temperature that I want. Okay, so now let's just say that my house gets to 74 degrees. All right, so here's 74. Great. Absolutely love it. That's what I want. That's what I want all the time. Thank you. So let's say that the house goes back up to 75. It's no longer 74, is it? No. Oh my God, it's hot. Turn the air back on. I mean, I hope you're not one of those people. I hope that you can tolerate a few degrees of difference when it comes to how hot your room is or how cold your room is. But there's a question here that we've got to ask, and the question is, when does the air conditioning cut back on? That's a good question. If it goes to 75, does it cut back on immediately and cool it down to 74? Or does it wait to 76? Or does it wait to 77? Or does it wait to 78? Like, what's going on here, right? Like, how hot does it need to be in order for that system to cut back on? Because that is an on-off position, an on-off control. How hot does it have to get for it to cut back on again so that way it can try to reach 74? Okay, well, let's be really nitpicky about it. What if that temperature of the room went to 74.5? That's not your set point. Your set point 74. So at 74.5, does your air conditioning turn back on again? And if it does, like, how long would that actually take it? Are we talking about your air conditioning cutting on like every 2 minutes? Nowhere in any world that I know of does this kind of situation happen. We don't want it to happen in the manufacturing line either. And the reason is because on and off switches, if you're not very careful, can damage your equipment fairly quickly. And that's because it makes it work harder. So what normally happens here is, let's say that we set at 74, and let's say that I use my auto feature on my thermostat. So if my room gets too hot or if my room gets too cold, the heating will cut on or the air conditioning will cut on. That's great. So what's going to happen here with the auto is that I have determined a set point, and that set point is 74. Well, there is going to be kind of a maximum temperature and a minimum temperature that my air conditioning and heating system will utilize from that thermostat before it cuts on and does any other work. There's no in between. It's either off and on, and I don't want it to cut on every few seconds or every minute or every 2 minutes. I need it to take a break. I need it to rest. Cutting things on like this can actually, again, damage the equipment or the pieces and parts that make that equipment work fairly quickly. And I don't want to be buying a new air heating kind of system every year or every 2 years because I'm abusing on how I use it. So there's a maximum and minimum, and let's say that there's like a 4-degree window here. I don't know. So instead of 74, the max will go to 78. And when it goes hotter than that, then the air is going to start blowing and it's going to cool down the room. All right, well, my minimum, let's say that my minimum is going to be 4 below as well. It's a plus or minus 4. So let's say that goes to a 70. So if it goes below a 70, then that means my room is too cold. I don't want it that cold. The heat cuts on, and the heat will raise it back up to 74. All right, that is great. That is a window. And in this window, nothing really is going on, right? I mean, my air conditioning's not working. My heater is not working. It's just like off. And it's taking a rest. It's taking a well-deserved break because it has saved me from going out in the 100-degree weather and going, woo, it's hot out here. Woo, God. So this kind of span, this region of it not doing anything at all, this is what we call a dead band. Hopefully that describes deadband a little bit better than to stabilize control and reduce switching frequency. Systems are designed to prevent control action during a specified period of time, which is called the deadband. All right, so hopefully that will kind of get that idea of a deadband across to you. So again, many pieces of equipment are going to be used on the manufacturing line. Those pieces of equipment have to be taken care of. Those pieces of equipment can be on-off switches, and the problem is the wear and tear. How often are they turning on? How often are they turning off? And a deadband is going to be needed because of that. So here you see a graph, and that graph is kind of showing you what's going on, and they just so happen to use temperature as well. So let's say here is the set point, and my set point is that line right there in the middle. They use 70 degrees, but here's my room temperature, and that temperature, or let's kind of devise this in a bioreactor. That's even better. So let's say that I've got a bioreactor, and that bioreactor should be held steady at 70 degrees. Well, let's say the bioreactor is right here, and that's at 73, and that's a little too warm for it. So we send a little bit of cooled water through the jacket, and then we lower that down. And if we continue to send cold water through that jacket, well, there is a chance that that temperature will go lower and lower and lower. So when it goes too low, we know that there's a problem. We're a little bit below 70. That's not good. We want it to be warmed back up. So it will begin to warm back up, and then we can allow it to go a little bit above because we don't want to be that finicky. We don't want to be that picky. But if we go a little bit above, that's going to be okay. And then if we go too far up, then that system's going to cut on again. And it's going to go, uh-oh, we need more cold water, so send it through. So more chillers activate, more cold water begins to get pumped through, and the temperature begins to go back down. As you can see, that is a dead band. So the dead band of it not doing anything at all and just monitoring temperature, just making sure everything's okay, making sure everything is close to our set point, that is the dead band that we are referring to. And that dead band, well, we can kind of track, like, how long is this process kind of taking? That's kind of the other part of the story. So if we send cold water through this jacket and it plummets that temperature down, like, how long is it ideally, or on average, how long is it going to be before we've got to send more chilled water through that jacket again? So as we are performing these processes, we can gather that information. We can see what these average timestamps are going to be, and it gives us an idea of being like, oh, yeah, I see. So in another 5 minutes, it's probably going to go below that temperature, and we need to kind of cut it off. We need to allow it to warm back up, and that might take another 5 minutes. And then 10, 15, 20 minutes later, it might be time to get fresh chilled water to filter through this jacket all over again. Well, that's the off and on version. And as you can imagine, there's also another option, and that option is called proportional control. So this is not an on-off. This means that it is going to constantly look at data, and it's going to constantly make changes, so that way we can for sure stay at 70 degrees as close as possible, as often as possible. That is what a proportional control means. So any of these variables that we've talked about, pH, temperature, dissolved oxygen, any of those can be measured, of course, can be logged, of course. Automated systems can help us do that, absolutely. And in the past, I've said, well, when it goes above a certain level or when it goes below a certain level, well, there's a feedback loop, and that feedback loop is going to take a sensor and it's going to send a message to the transmitter, and the transmitter is going to go to the controller, and the controller is going to go to the controller flow control, blah, 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 blah. Okay, so you get the idea. But here in this type of situation, a proportional control is constantly on the move. It's constantly doing something, and it can do things in little bitty itty bitty steps. So it doesn't have to take a valve, and it doesn't have to open that valve wide open. It doesn't have to take pH runs, and it doesn't have to open the valve all the way to flood acid in or to flood base in. It is perfectly fine if it does it in little bitty steps at a time. So it could just trickle it in, and then it is monitoring what happens in that little bitty trickle, that very, very slow flow. It's going to look at what's happening to the data, and then if it sees that it's going above or under again, well, absolutely, it can just open it up just little bits at a time and take care of what it needs. So this is what a proportional control is versus something like an on and off control that you might see at other areas of the plant operating some other pieces of equipment. So it's not a big deal, and it actually is a good deal, because what's happening with proportional control is that it is not fluctuating as much. So if you do the on and off situation, we kind of want to give it some time. We don't want things just to start up every couple of minutes because, again, that could damage the instrument or the pieces and parts that make it work. So what's happening in proportional control is that it kind of is constantly on. I mean, it's not fully turning itself off. It's not fully turning itself on. I mean, it is slowing things down tremendously or speeding things up in order to get what it needs. So the fluctuation that we are talking about, let's say that we go back to that thermostat and that thermostat is set at 74. That means it is staying at 74 for the most part. It's not going down to 70. It doesn't even see it that far. It's not going up to 78. It's not going that far either. It is hanging around 74, and it's going to fluctuate, absolutely, but the fluctuation is not going to be major. So that could be a good thing, especially with these really highly sensitive processes that could take place in a manufacturing line. Next up, there's no dead band. So there's nothing there where we are saying, oh my God, it's taking this much time in order for it to turn off, turn on, in order for it to give it some time to rest and blah, blah, blah. It is, again, constantly on, constantly doing things and keeping it at 74 as much as possible, if that's my example that I'm using. It's also more precise and it's also more stable. So what happens with proportional control is that it's more precise, meaning if your cake direction said 350 degrees, it better stay at 350. There better not be a lot of fluctuation in your oven. If there's more fluctuation in your oven, then things are going to cook hotter and things are going to cook cooler. And by the time that your timestamp is done on your recipe box, it's going to turn out awful. It's not going to be a nice little fluffy cake. It's going to be a burnt brick if you're not very careful. So the precision tightens up on proportional control, and they are also more stable. So you don't actually have a lot of problems out of these things. They are constantly running, they're constantly doing their thing, but even in the laboratory setting, there's a few pieces of equipment that if we turn them off and turn them on, and turn them off and turn them on, and turn them off and turn them on, the startup and the shutdown is actually a little bit harsher on all of the gears and mechanisms that make that thing work. So that could be bad, and these proportional controls will put a stop to all of that madness, so that way it's not that hard or difficult on the machine. Next up, we talked about this window of it not doing anything at all. Well, there's two other terms here that we can also bring into the picture, and one is called dead time and the other one is called lag time. So I'm going to go back here, and this was called dead band, and the reason is that band was actually a kind of window of opportunity here where things were not working, things were off, things were not doing anything at all. So that was the dead band. It was just a window that was kind of acceptable here in a roundabout way. But these two terms are slightly different because one is called not a dead band, but dead time, and the other one is called a lag time. So these are two things that we want to look out on the manufacturing side as well. If I read the directions or the definition of dead time here, it says the interval between when a disturbance changes the process and when that control loop can make a correction. So in the dead time, nothing is happening at that moment to correct the process. It is just to relay the signal. I mean, that's pretty much what it is. All right, so let's say that I get a disturbance. All right, so that disturbance, my DO level begins to go low, 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 and then it goes so low, and we're like, oh my God, I need dissolved oxygen or my colony is going to die. Please, please give it to me. So that DO level that we are trying to pump into the bioreactors, well, those types of situations have to be done. And there's probably an alarm that's going to go on. And that alarm might need you to manually go in and do it yourself, or that controller is going to send something to a piece that's going to be able to do it for you. Either which way, it does not matter. But when that begins to plummet, and when the controller understands that this is a problem and it has to be fixed, that is what we call the dead time. So from the moment that it does go too low to the moment that that controller gets that information and it says, oh my God, something is off, that is going to be the dead time. So this does not include it actually trying to fix itself, because that's now in action. That is actually actively trying to fix the problem, and no longer is that dead time anymore, but that is work time. It's actually working to solve that problem for you. Now, lag time is something a little bit different. Lag time basically means from the moment that you get, in this case, low DO, low DO, low DO, low DO. Okay, so by the time that you get that alarm, by the time you get that alert, that sensor, that transmitter, it sends it to the controller. The controller might go ahead and activate whatever needs to be fixed or whatever needs to be done. It might take care of that for you. But there's going to be that dead time involved, plus by the time it opens up a valve or what it needs to do, by the time it rushes something in, by the time it fixes the problem, well, all of that is also time that needs to be kind of discussed and needs to be brought into the picture. So that is what lag time is. It is the definition of the dead time, because that's the time that it took for the controller to recognize something needs to be fixed. And it's also going to include what I would call the action time. So that action time is for that valve to open. That action time is going to include that fluid from coming in. That action time is going to include, well, now that we're getting the fluid, how fast is it going to be before we get back to the appropriate levels, in this case of dissolved oxygen, that we need in that bioreactor. So all of that is time that is very important, and it is the entire thing. From the time that we get an alert, from the time that it fixes itself, that is what we call the lag time. So lag time does include the dead time. That is not two totally separate things. Dead time is just by the time the controller gets it and understands there's a problem. And then lag time is from the moment there's a problem all the way to the moment that it is fixed. That is the difference between dead and lag time. Next up, we're going to talk about PID. PID stands for Proportional Integral Derivative Controller. So PID. It's probably a definition that's going to show up in a quiz or some type of online assignment, and it might say, what does PID mean? Or why would you use a PID? Blah, 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 blah. Well, PID, Proportional Integral Derivative Controller. It is a loop feedback, and we've talked about what loop feedbacks are. It is this whole idea that, hey, I've got a sensor, I've got a transmitter, I've got a controller, and then I've got the controller or the flow controller, or whatever the case might be. So it is continuously monitoring, it's continuously taking care of the situations as they begin to get out of specification. So the PIDs are constantly monitoring and constantly adjusting these types of things. That is kind of the formal way that we term them, that way we brand them, the way that we talk about them, and that's what that kind of abbreviation stands for. I think another thing that people tend to forget about here is that very often we need to make small changes, not big ones. So if stuff does go to, let's say, that pH of 4 when it should be a 6, then we shouldn't flood everything in at one time. And the reason is because we might overshoot it. And if we overshoot it, we now go on the other side of the house, on the base side. And if we're not very careful, that actually could be way worse than having it at a pH of 4. So whenever we get something that's out of specification, again, whether it's DO or temperature or flow rates or whatever the case might be, we want to make really, really tiny changes at a time. And we want to give it enough time in order for that to try to correct itself. And that's the problem. People are not patient because they think the plant's going to blow up. It's not, we promise. These alerts are in place for a reason, and they are giving you time in order to fix situations. And you know, even if you fixed it and made it just a smidge a little better, then it's better than what it was before when the alert went off. So if it was a pH of 4 and you did something and that pH now went to 4.8, well, it's not 4, it's actually getting closer to 6. So good job for you. You made it better than what it was. And if that means that I need to go back and add like a little smidge more, then I'm going to allow that to kind of take over. I'm going to allow that to do its job. And then I'm going to give it time to actually work. The other thing that's going to be very important here, I think that one person, needs to be responsible in making these changes. And it's like too many cooks in the kitchen, right? I mean, if you're in the kitchen and you're cooking a nice dinner for somebody, you do not want to be impeded with all of these other people that are trying to do their own thing. It just not enough room. There's too much chaos. No one knows what's kind of going on. People are going to get done at different times. There's no planning that can be involved. But if there's one person actually cooking the meal, then they can juggle what they need to juggle. They know what needs to come up, and it's going to be a little bit better situation on your dinner plate because of it. The same thing happens in the manufacturing line. When these people are assigned in order to fix a problem, that person needs to fix the problem. 4 or 5 people do not need to be working on this problem at the same time for the most part, because one person is going to make a change, and then these other 4 or 5 people could also be making changes. And then by the time it's all said and done, it could be too many changes, and now the whole system's out of whack. I mean, now you're talking like, I'm at pH of 14, yeah! So it's just not going to work. So one person makes small changes, wait for those small changes to take place, and see how that affects your results, and your sensors are going to let you know that. So remember, adjustments in one process can affect other ones. So what you are doing in this step later on down the road can actually affect those as well. Or what you're doing in this process can actually affect other things that you're trying to measure at that particular stage of the process. Okay? So if you measure temperature and the temperature goes wacky, then there is a chance that once you get your temperature fixed, because of what had happened, something else is now wacky that you will have to kind of fix and take care of as well. So again, when one alarm goes off, many can go off. Just be ready for it, because that's going to be kind of a problem. Some common problems here. I think that when people are on the manufacturing line, one of the things that they do is that they adjust more than what's required. So what that means is that they kind of, again, overshoot it. And it's like kind of making a pot of soup at home. I mean, you're making some, hopefully wonderful, vegetable, healthy soup. And you're like, I've got this. This is going to be so much better than Campbell's. And if you're using Campbell's as a comparison to go by, I am so sorry. Either way, I can give you some good recipes. I might leave out a couple of ingredients because I still want mine to be better than yours, but I'll still give you some good recipes for some soups. Either way, if you're in the kitchen, you're making these soups, and you're like, there's just something missing. What do I need to do? Well, I'm going to add some salt. Okay, well, don't add a whole palm full of salt, because by the time that salt goes in there, you have done more than what was required, and then you're going to taste it, and you're going to go, oh my God, who made this soup so salty? I don't know why it turned out so salty. And then you'll go in and you'll make excuses to everybody else, and you'll blame it on something, and they won't ever know the difference. Or you probably have heard, well, drop a potato in it and it will soak up the salt. Does that work? Who knows? I'm not going to tell you. I'm going to let you ruin it. But I hope you don't ruin it, because I hope that you make small seasoning changes, little bits at a time. And I hope that you treat the manufacturing line the same way. Small changes, little bits, give it a taste test. And then if it needs more, add more. But don't overkill it or overshoot it, please. Next up, making a second change before the first one is fully complete. So again, if something's quite off of your soup recipe, you don't want to add salt and pepper and garlic and onion and just dump in the whole seasoning spice cupboard. I mean, you kind of do them little steps at a time. So add one seasoning, give it a taste test. If you think something else is needed, hence a second change, then add that at a different time. But allow your seasoning to fully dissolve and go in solution. Look, I'm being all sciencey with a kitchen and a soup kettle. Who would have ever thought? But allow those seasonings to take place. Allow those seasonings to incorporate before you add your next one. Also, keep in mind, dead time and lag time are a thing. Hello, we just talked about this. Oh gosh, dead time and lag time. So by the time you add the salt to your soup, it's going to take a little bit of time for it to fully dissolve. Don't taste test it immediately after. Give it some time. Allow it to do its job. There's going to be a lag in place. And that lag is also going to be, okay, well, what's kind of the next seasoning? Well, taste test it first before you add that second one in. And again, it's going to take that one time in order to settle and in order to fully incorporate. Finally, I would say the more complex the process, the longer your wait time should be. So that is something that we need to keep in mind. These are very sophisticated steps in some of these types of manufacturing facilities, and small little changes can really make a major impact. But because they're so complicated, you really do want to give them time to settle down and do what they need to do. There are so many puzzle pieces that are moving on the board, or chessboard pieces that are moving on the board. I don't know, whatever analogy you want to use, you know what I'm trying to say. But there's so many moving objects that we've got to take care of in the manufacturing line that one little change can make an impact. But again, I've got to give it time. And the more complicated, the more moving parts, well, the more time that I want to give that before it settles down. Absolutely. Variation, there's two different types of variation, and then we're almost over with this lecture video. Two types of variation that we're going to find: normal and special. Normal process variation, well, that's normal. It's going to happen. It's natural. It's expected. So, for instance, changes in pH, right? So we are growing stuff, or we are adding things into vats, and that pH can change over a course of time, or as that material begins to use whatever we give it. That's not an issue. We know what's going to happen. Again, it is expected. And if it goes below or above a certain level, then an action is going to be taken, and an action is going to fix that and get it back in line. Special cause variation is something that's not normal and something that just comes out of the blue. Oh God. And then I've got to deal with that at a little bit later date, or immediately, but I've got to deal with it. And this is something that I don't normally see. So for instance, let's say that I am out with my little doggy and I'm out in the yard, and I'm letting him enjoy the nice little sun, and he's sunbathing, and he's going around, and he's trying to find creatures to eat, or he's decided to eat dirt, or he's decided to roll around in a big anthill. I mean, you know, maybe these are things that he enjoys. Well, this is the normal process, and there's going to be variation there. Some days he might not want to roll in the anthill, and some days he might. So these are things that we know is going to happen. We knew it before we even took him outside what he was going to do, and we just allow him to kind of go to his own devices and just do whatever, and these are the things that he kind of comes up with. All right, so if that's the case, this is normal process variation. Nothing to be alarmed with, because it was something expected. And then let's say that one day I take him out and he's just doing what he does every single day, no matter what. And then all of a sudden a hawk comes down and grabs hold of him and flies off with him. Yay! Yay! All right, I don't have to worry about them anymore. Okay, I'm not that cold-hearted, but that was a random thing that happened on that day, and that is a special cause variation. Something changed, and it was drastic, and it was unexpected, and we've got to figure out how to fix it. All right, so these are things that are not normal. They randomly happen, but it can also be a consistent, steady, what we call upward, or a steady downward trend. So here's a graph, and this is just normal process variation. So again, I'm going to get some fluctuation. This green line here is the set point, and then up here, this red line could be like a max and a min, if you want to think of it that way. And as we are doing our manufacturing process, we are gathering data, and that data is getting dumped into a computerized software or some type of spreadsheet, and we get these graphical kind of analysis that comes out of it because of that. Well, okay, this is normal process variation. Temperature will fluctuate. DO will fluctuate. pH will fluctuate. Flows can fluctuate. It's not a big deal. So, whoop, 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 whoop. Notice that sometimes it can go really high and sometimes it can kind of go low, but at the same time, it never crosses those thresholds. It's not a big deal. That is normal fluctuation. It's going to happen. It's going to be there, whatever the case is. This is kind of like the temperature of my room, right? It's going to go down, up, down, up, down, up, down, up. But there's going to be a point where sometimes, maybe sometimes, I'm going to be in that room and I'm going to be like, oh my God, it's so hot. Like, what's happened? I mean, this is definitely not 74. I mean, I'm sweating sweat beads in here. Did you do something to the air? Did you turn it off? Or is our air conditioning messed up? We've all had those moments probably. Well, this is special cause variation. Something has went wonky. Something has messed up where now it is fluctuating, but it has fluctuated to the point where it is whoop out of the parameters that we have set. So this is special cause. That is what we call this. And that means that things are not fluctuating according to plan and things need to be fixed. Also, an upward or downward trend is another sign that something is kind of off. Fluctuation should be natural. It should go up, down, up, down, up, down, up, down. But here, after this 10 mark on the x-axis, you see it go up, 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 up. That is not normal. So fluctuation definitely means fluctuation. Fluctuation means up and down, up and down, up and down. Whenever we see long periods of constantly values going up or constant values going down, that is not fluctuation. That means something is getting ready to happen, and I need to figure out what that is before it gets worse. All right, so that ends section 6.8, and we are off to section 6.9. And guess what, folks? This is our last section, which means that next video might be your last one. Oh, it's time to celebrate and go have a drink if you are legal drinking age.